Hi there, I'm Nix, and the topic for today's video is solving the height checker problem on the LeetCode website. As always, I'm going to solve this problem in the C++ language and give you a detailed explanation of the entire process, from the planning of the algorithm to the coding of it to the analysis of time and space complexity and looking at the LeetCode rankings. So if that sounds interesting to you, then stay tuned. Welcome back. A bit of housekeeping before we get into things. Last time I solved the sort array by parity problem, and now we're moving on to the height checker. So we've skipped over remove element here, and it has an orange check mark. Well, that's because we already solved the remove element in a previous section of this explore card, and we found an in-place way to do it as well. So there really isn't anything to do for this problem since we've already solved it. So that's why we're skipping over it, and the reason why it's orange instead of blue is whenever you solve a problem in, say, a previous section of the same explore card, a different explore card that you've solved in the past, or just going through the problems that LeetCode has and solving it independently. You solved it in the past some way, but you haven't specifically solved it on this particular area of the website, so it has an orange check mark as a result. Moving on. So we have a school, we have some students, and the students are asked to stand in a single file in non-decreasing order by their height. So the ordering could be represented by another array that's called expected, where the value in the expected array is the height of the ith student in line. So we're given an integer array that's named heights, and that represents the current order that the student is standing in, and that may or may not be correctly sorted. They're zero indexed, and here is the money statement. We want to return the number of indices where the value in the height array is not equal to the value in the expected array at the same index. So looking at the examples here, we are given the heights array here, and we go through this array and we compare it to, say, an array that has everything in the proper place. Well, 1 to 1, that's good. Another 1 to 1, that's also good. But here we have a discrepancy. In the expected array, we have a 1, but in the height array, we have a student with height 4 in this position. That's not the right position where he's supposed to be. So that's a discrepancy, that counts. The 2s are in the correct place, but 1 versus 3 and 3 versus 4, both of these students are not in the proper place. So that's why the output is 3. Again, here we are given the heights array. In this case, everything is in the wrong order, and every single student is in the wrong position when compared with where they should be in the correct sorted order. So all 5 are mismatched, so the output is 5. And of course, if we're given a height array that is already sorted, then everything is in its proper place and the output is 0. Looking at constraints here, we're dealing with fairly small ranges. The length, we're never going to be given an empty array, and it's going to go from 1 just to 100. And the heights that are possibilities can range from 1 to 100 as well. Now, what probably first popped into your mind is probably the intuitive way of solving this, where, as we did in the example, we have that height array. We make a sorted array that we can use to compare to. And every time as we're going through the array, we reach a comparison in which one index has a different value than the same index in the other array, we record that as a mismatch. Once we go through the entire array, we're going to be able to find all the discrepancies and we return that value. Let's go through coding that way, and then let's move on to more interesting territory and cue foreshadowing. First up are the variables I'm going to need. I have an integer variable that I named count mismatches, and I've set that to 0. And I've created a new vector of integers. I named that expected heights, and I set that equal to the heights array. Next thing to do is sort expected heights, and we can just call the sort function that's built into C++ and go from the beginning of expected heights to the end of expected heights. Now that we have a sorted array to compare to, let's go through the initial array from the beginning to the end. And if the value in the heights array is not equal to the value in the expected heights at the exact same position index that we're looking at, then that is a mismatch, and we're going to count it by incrementing that variable up by 1. Next up is after the for loop, we're going to return that count because the function expects a return value that's an integer. And with that, this code shouldn't have any errors and should work, so let's go through and verify that. 3 is equal to 3, that's good. Let's go for the full shebang. And accept it. Excellent. Looking at the time and space complexity of this thing before we click the button to view rankings. This requires constant space since it's an integer variable here, but this requires variable space. We're making a new container that is going to be dictated in terms of its size by the size of the heights array, the input array. So because this thing exists, the space complexity of this algorithm is going to be equal to big O of n, where n is equal to the input array size. In terms of time complexity, this for loop is dictated by the input array size. So this would have a dependency of, say, big O of n, but this sort function has a larger time complexity attached to it. The sort function has a time complexity of big O of n log n. And because in time complexity analysis we only take the largest term, this for loop goes by the wayside, and this sort function, which has a time complexity, is the one that dictates the time complexity of the entire algorithm. So big O of n log n time complexity and big O of n space complexity. Now let's look at the rankings. Okay, not too big of a distribution, which makes sense. This might just be lag or server traffic, something. But in essence, all of the possibilities are bunched up into a very small range, which makes sense because with this problem, the maximum size of the array is only going to reach 100, and the potential values that are present also have a small range. So because the size of the array is really small, even if you have different algorithms that have different time complexities attached to it, because the input size is so small, they're probably not going to be big enough to be able to see the differences in that situation. Okay, so we have a "you are here" sign for the memory usage, and again, it's really small range here. So again, because the constraints of this problem restrict it to such a small range, we're probably not seeing too many differences in terms of distributions, even when different algorithms may exist that have different space complexities. Alright. This was the intuitive way to do things. This was the thing that probably first popped into your mind when you read the problem. But how likely in a technical interview are you going to be allowed to use the built-in sort function in C++? Not likely, right? Right. So let's go through this problem again and solve it in a way that doesn't require use of the built-in sort function. So how are we going to do that? Well, what I keyed into that led me down the line of thought toward a second solution was that these heights that are all possibilities have a very small range to them. It's only from 1 to 100 in increments of 1. So with that limited range of possibilities for the students to have in terms of their height value, that leads me to a different way to approach the problem. So let's bring up my handy dandy whiteboard and let's walk through some examples here. So let's say we have a vector, and this vector is big enough in its size to be able to handle all of the possible heights we could ever see for students. So if we also throw in a value of 0 to make all of the indexes equal to the height that we see, then this array would have a size of 101. A 0 value would be in the 0 position, and then it would go from 1 all the way to 100 and have every height in between. So 1 to 100 plus a 0 for the start would be 101 in size. Now let's take this vector and imagine that it serves as sort of a checklist, where every time a student comes in to form that height array, we're going to take a look at that student's height and record that value. So this array is going to serve as a count of all of the heights of the students that we see. So as an example here, let's say we have an initial height array that is like this: 99, 1, 2, 2 98s, and a 100. Now we go through this count array and we record all of those heights. At the 0 index position, a value of 0, because at no point in time is a student ever going to come into our view and have a height of 0. But we have seen a student with a height of 1, so at index 1, we record a count of 1. Same with the student that we see that has a height of 2. At index 2, we record 1. Now at 98, we're going to have a value of 2 present because 2 students are present with that height. And 99 and 100 are also both counted, so those respective indexes also have a value of 1 present. So this array is going to house all of the counts of the student heights that are present in the array that is given to us, heights. Now from this count array, where we have zeros in all of the places present where we did not see that height, and the correct count for all of the heights that we have seen, we can use that array to build a separate sorted array and eliminate all of those zeros. Because as we go through and walk this array, we see a value of 1 at index 1. Well, that value is present in the original array, so let's add its index value, which is going to equal the height of the student, into that sorted array. So because we see a 1, index 1 is added. We move on, and we see a non-zero value at index 2. So index 2 is then added. And as we move through the array, we're going to then see, eventually, 98 appearing twice. So add 98 twice to the array, then 99, and then 100, and we can see that we can build that sorted array from that counting array. Because that counting array is big enough to hold all of the potential values to see, and we've recorded which ones that we have seen. Now that we have the sorted array, this essentially devolves into this section right here, where we go through the original array and we will compare the height at the index we're currently at to the value in the sorted array at the same index value. And if they're different, we know that's a mismatch. Once we go through the entire array, we can return the count of the mismatches. Now, going through this problem, we can see that the initial counting array here doesn't technically need to go all the way to 100. It only needs to go until the maximum height present in the array. For example, if we have, say, an array like this, where the maximum value is just 50, well, everything beyond 50 in that counting array is just wasted space. So if we go through the heights array find the maximum number, we can go ahead and set that counting array's size to whatever that maximum is plus 1, again because of the addition of 0 at the beginning. So that saves us a little bit of space, but conversely, that requires a little bit of extra time because we need to go through the array heights initially and find whatever the maximum is. So that step is good if you want to kind of optimize a little bit your space usage and you don't particularly care if it takes you a little bit of extra time to go through the height array in order to find that maximum. If you do care about the time requirement that takes, then you can just make count equal to the maximum possible height you could see. If you don't care about that additional time requirement and want to maximize your space usage as much as possible, then you can spend some extra time and find that maximum. With all that being said, let's go through, reset this, and go through the coding. Okay, first up is some of the variables that I'm going to need for this algorithm, and I've put in a comment here with an example of a heights array that we're going to use as we go through the code. So, much like before, we have an integer that I've named count mismatches, and I've set that to 0. I also have an integer that's called max height. Set that to 0, and I have an integer that I've called sorted position, and I've set that to 0 as well. Finally, I have one of the two vectors I'm going to need to create. This vector of integers I've named sorted heights, and I've set the size of that vector equal to whatever the size of the initial input array is, because this heights array is going to have every value that's eventually going to show up in this array too. So those array sizes will always be the same. Next up is the loop. As this integer variable has indicated, I'm going to go ahead and go through the array initially, find the maximum, and use that maximum to reduce some space usage for the second vector array that I'm going to use. So to do that, this is arranged for, and for every value of height that's present in the array heights, if that height value is larger than the max height variable, then I'm just going to set that maximum height variable to that value. And as it goes through the array, it's going to record what the maximum is. And then for this example here, as we go through, it's going to find 12 is the maximum height and set it to that value accordingly. Next up, as this comment explains, is when I create the second vector I'm going to need. This is the one that's going to house the count of the heights. And initially, I'm going to set that size equal to whatever the maximum height I found in the original array, plus 1 to make room for adding a 0 at the beginning. And I'm just going to fill that array initially with zeros. So this is what the count of heights array is going to look like for this example here. The maximum size is 12. It's going to be set to 12 plus 1, or 13. So here we have 3, 6, 9, 12, 13 zeros. So completely filled with zeros, size 13. Next up is a loop that is going to convert this count array and actually fill it with the count of the heights that are present in the heights array. So to do that, again, arranged for, and for every value that we see height in the heights array, we're going to have the count of heights value at the height index increment by 1. So execution of this statement here is going to go through the array, and we see a height value of 1 in heights array. So the count of heights value at the position index of height 1 is going to be incremented up by 1. So that is why this value here is a 1. That is why the 7th index here is also a 1. Because it sees 7, it plugs the value height of 7 in here. So the count of heights at that index position of 7 is going to again increase by 1. So again, goes from 0 to 1. Then we see a 4 increments up by 1. And then we see 2 consecutive 9s. So at the 9th index here, it increments up by 1. And then when we see it a second time, that same index's value is going to increase by 1 again and go from 1 to 2. Index 12 is going to increase by 1. And when we see the second 4, the 4th index is going to have a final value of 2. So this for loop goes through the entire array, counts up all of the heights, and records it in this array. This next loop is now going to create the sorted array from this count array. So we're going to start from the beginning of the count array and go until we've reached its end. And every time we see a non-zero value in that count array, we're going to do stuff. We're going to set the sorted heights array value at the sorted position index and set that to the current index that we are at in the count of heights array. We're then going to increment up by 1 that sorted position, and we're going to decrement down that count of heights value at the current index we're looking at. And then we're going to perform another check. And if the count of heights value at the current index is still greater than 1, then we want to reduce the index value by 1. So let's go through this example and see how this execution of code creates that sorted array. So we start at 0, and let me record all of these things that we care about. Okay, we have the index, we have the sorted position, and we have the count of heights and all of its values here. So let's go through and build this sorted array. So we start at index 0 and we see, well, a 0. So this doesn't fulfill the if statement, so we just skip over that. The for loop comes back around, index increments up by 1, and we go through again. Now note, the index has changed with the for loop, but our sorted position value is still 0. So now we are seeing a non-zero value. So this if condition is true and we want to do stuff. So now we're going to set the sorted heights array value at the sorted position equal to the index that we're currently on. So that means that we're looking at this value to fulfill the condition. This value is at a current index of 1, and we want to add that index value to the sorted heights array at the sorted position, which is 0. So add 1 to the beginning of the array. Now that we've done that, we don't want to overwrite this value, so we want to move on to the next position in this array, so we want to increment up sorted position by 1. Now we want to decrement the value of the count of heights array. So the value is right here, and we want to reduce that by 1. So that zeroes out. Now, this if statement, we check to see if the condition is true. Well, the value that we are currently at with an index of 1, well, we're now 0. So we never go into this branch and we move on. We go through and we see some zeros. And the next time something interesting happens is when we are at an index of 4. That's when we see the next non-zero. This time we have a count of 2. So we go through, we want to add the index value that we're currently on to the sorted array at the sorted position here. The sorted position is 1. The value we want to add is the index value of 4. So 4 goes there. We increment that up to position 2 because we don't want to overwrite what we've just written. And we go through, we've done this step. Now the count of heights value is decremented by 1. So 2 now becomes 1. And now is an example of when this if statement is going to execute. So this if statement, we are dealing with the count of heights value that's still equal to something that's above 0. So we want to decrement the index that we're currently on. and we want to push it back by 1. Now the reason why we do that is now we've reached the end of the code here, and when we loop back around, the index will go up again and bump us back to where we just were. So essentially, this code here functions as a way to freeze the position in place if we are at a value that has occurred more than once. And it's going to ensure that that index value is added as many times as it was seen in the original array. So here we go through the full shebang again, and we're going to add another 4 here with the sorted position going up and this zeroing down again. Now we move on, and as the same thing occurs, we're going to add a 7, reduce that. We're going to add 2 9s, 9, 9. That will eventually zero down. And the last thing to add is a 12. And now our checklist has checked off everything to add, and we have now built our sorted array. Now we've gone back into familiar territory. Since we have this sorted array here, we can essentially do what we had to do in the previous solution. We go through the heights array and compare the values to each other in the height array and in the sorted heights array. If they're not equal to each other at the same index position, then that is a mismatch. We count that, increment by 1, and then at the end of the height array, we have an accurate count of how many students are in the wrong position, and we return that value. So this entire code should handle everything that's thrown at it. And let me verify that there are no errors and that it actually works. Judging 3 to 3. Submit for the full shebang. Judging and green text. Yes! Okay, now that we know it's accepted and it works, let's go through time and space complexity analysis before we look at the rankings. So here, in terms of space complexity, we have some constant space variables here. What is going to dictate the space complexity and what we have to look closer at are these 2 vectors here, because they are the ones that are going to take variable space. Now this one is going to take up a memory amount that's equal to the initial heights array. So this would have a big O of n space complexity for this portion, where n is equal to the initial input size. This one, however, depends on a slightly different thing. This array will have a size that is dictated not so much by the size of the heights array, but by whatever the maximum height is in that array plus 1. So that we can set equal to another variable that we call m. And because we have made 2 arrays here, the space requirements for these vectors are additive. So the space complexity is going to be equal to big O of n, where n is equal to the initial array size, plus m, where m is equal to the maximum height present in that array, plus 1. Now let's move on to the time complexity. Now going through here, we only see for loops. We don't see anything nested. But beware, if you just go with the general guidelines of, oh, hey, for loop means big O of n, right? No, not in this situation. This algorithm does not have a big O of n time complexity. It's more involved in that. So let's dig in and go through the loops individually. This one goes through the heights array, so it's dictated by the height size. So this portion here does have a big O of n dependency. Same for this for loop here, which is another big O of n time complexity as it goes through the heights. So the number of times it executes and the number of loops it goes through is dictated by the size of the heights array. Same for this for loop down here. Again, we're going from the beginning to the end of the heights array, so it's dictated by the heights size. However, this for loop right here depends on something else. Now, let's take a look at this for loop with some extreme cases where we have a height array that, say, looks like this. This extreme case will essentially make the count of the heights array its maximum possible size. It will go from 0 all the way to 101 in terms of its indexes. And this for loop is going to go through that, and it's going to see 100 zeros, and then at the very end of it, it's going to see a value of 1 for that one student that is a super duper tall person. So it'll run 100 times, and even though it's technically not really executing additional lines of code except for that very last time, it's still performing a loop. It's still reading what the value is in the array, and it's still determining whether this if statement is true or not. So that read and if statement determination is an operation, and it still technically counts. So it's going to execute about 100 times, and will depend only on that count of heights array size. However, let's look at a different extreme here with case 2. Now here is a different case. This is the other extreme, where we're given a heights array that has the maximum size to it. It contains 100 things, but every single value in this array is the same thing. So imagine 100 students walk in, and they all have a height of 1. Now, what does this for loop do as a result? Well, in this case, the count of heights array is just going to have a size of 2. It's going to have that initial 0 value for the 0 index, and it's going to have a count of 100 in the index of 1 position. Now, this count is going to be really tiny, but this for loop overall is still going to execute 100-ish times, because as soon as it skips over that first 0, it's going to see that second value equal to 100, and it's going to go through, and this if statement is going to keep resetting the index, so we go through all of those duplicates. And as a result, you see the two different dependencies that this for loop has. It'll depend on the size of the count of heights array, which is equal to the maximum height plus 1. And it's also, because of this if statement, going to depend on the number of duplicates that are present in that count array. So as a result, this is going to have a time complexity equal to big O of n for these additional for loops here, plus m, where m is equal to the maximum height plus 1 plus the number of duplicates present in this original array heights. That's how many times this for loop is ultimately going to run. That's what this is thus dependent on. So a little bit more complex than the typical generalization of, oh, see a for loop, it's equal to big O of n. And this problem is a good example where those general rules of thumb for figuring out time and space complexities are very useful, but in order to make sure that you get the answer right every time, you really have to dig in deep and really look at the code and see what it's doing and what it's dependent on. And just like for this section here, while you're going through and figuring out how many operations it does, a good thing to do is to look at the extremes, as I did with those two test cases of the heights, one having just one thing in it, but it has the maximum possible value, and the other one, it has the maximum possible length, but it all has one value. So that's a good way to kind of poke at the code and see what it's doing, to have a really good understanding of it in order to understand how many operations it goes through, and thus what the time and space complexity of something would be. So both time and space complexity have big O of n plus m, but those variables mean two different things. In the space complexity, m is equal to just maximum height plus 1. In the time complexity, that's equal to maximum height plus 1, plus the number of duplicates present in the array. Now with that, let's go and see if I show up here. Okay, we are down here in the void of nothingness again, and it has not registered the "you are here" sign. Okay, went through it again to try to see it register, and it held me in the void of nothingness and had a you are here sign actually show up. And I've seen it ping pong around here, so again, with this range and how small the constraints of the size are for this problem, it's hard to differentiate among the LeetCode rankings. That was the height checker problem. I hope you've got something useful out of this video. Thank you for watching, and as always, I will wish you happy coding and to have a